All right, so the limit of a function f as x approaches c, it's the value the function approaches as x approaches c from each side. And we're going to look at that element there from each side as we work through some of these, okay? Well, let's look first of all at the notation, all right? The notation for a limit, we would read this, the limit as x approaches c of f of x. The limit as x approaches c of f of x. And let's look at what this actually does here, okay? Here I have a function f of x equals x squared plus 3. And I want to find what the limit is as x approaches 2. All right, so I would read, the way I would read this is in red down here. The limit as x approaches 2 of x squared plus 3. All right, well, first of all, let's look at this on a graph. This is just the parent function, the quadratic parent function, shifted up 3 spaces. All right, so I'm starting at the point 0, 3. I go over 1 and up 1 on either side. I go over 2 and up 4 on either side. I could go over 3 and up 9 on either side as well, but this is good here. All right, so here's our parabola. Okay? So what are we looking for? We're looking for the limit as x approaches 2. All right, so here's x equals 2 right here. So what we want to look at is our function on both sides is approaching this value where x is 2. Okay? And as we come from the left here, the value of our function approaches 7. Okay? As we come from the right, the value of our function is decreasing, but it's also approaching 7. So in this case, our limit would equal 7. Now, that's the same thing that you would get if you just plugged 2 into the function. 2 squared is 4 plus 3 is 7. And we'll look later on here at when can you just evaluate the function to get the limit, and when do you have to do some other stuff. Okay? So, we'll work towards that. In this case, we could have just plugged in 2. But again, we'll see why in a few minutes. Now, you'll notice I looked at the function as we approached from the left, as we approached from the right. Those two things that we just looked at actually have a name, and this is a significant aspect to this. Those are what are known as left and right hand limits. In our definition, we said it's what the function is approaching as we approach x from both sides, or from each side. Okay? So our left hand limit is the limit as x approaches c from values that are less than c. And the notation we would use here would be limit as x approaches c, and the left-hand side of our x-axis is the negative side, so after the c we put a little negative sign. Okay? It's not negative c, it's we're approaching c from the left. Okay? Our right-hand limit, we're approaching from values that are greater than c. So we take the limit as x approaches c, and we put a little plus after it. Okay? That says the limit as x approaches c from the right. So why do we care about this? Well, let's look at an example a little different than the first one we started with. Here we have our parent function, the rational function, 1 over x. You guys know what that looks like. It has an asymptote at 0, okay? So this is what that would look like. Now, as we'll see later, if we're finding the limit as x approaches anything except for 0, we could just plug in that value. If we wanted the limit as x approached 5, we could just plug in 5, it's going to be 1/5. If we wanted the limit as x approached negative 10, we could just plug in negative 10, and it would be negative 1/10. Okay? But because we have this, when we want to find the left and right hand limits as x approaches 0, okay, we have to use those in order to determine what the limit would be as x approached 0. Okay? So when we're finding, I just called it the regular limit, the limit as x approaches 0 of 1 over x, we have to first consider the left-hand limit and the right-hand limit. We're going to actually use this to develop a theorem, our first limit theorem. Okay? So, take a look. As we come from the left-hand side, as we approach 0, what does the value of our function do? What? It decreases. Okay, and where does it stop? It doesn't. Okay? So we would say the value of our function is approaching, there you go, negative infinity. Okay? Negative infinity. It's just going to keep getting smaller and smaller and smaller the closer you get to 0 on the left-hand side. Now let's think about the right-hand side. As we come from the right, our function increases. So that's positive infinity, yeah. Okay? So now let's think about our definition again. The limit of a function is the value, singular. Okay? Well, here we're approaching two different values. So what would we have to say about the limit itself? What do you think?
Plus or minus something? No.
Not a bad thought, but that's two different values, right?
Yeah.
Well, but it's not approaching infinity from the left side.
So there is.
It's undefined. There is no limit. Okay? And what we could say here, and this actually is used a lot, you'll see DNE, does not exist. Okay? The limit does not exist. If we're approaching two different things. Okay? Now, if we had plugged in 0, it would have given us something undefined. That doesn't necessarily mean, though, that the limit will be non-existent. Okay? It does mean, though, that we need to do some further looking into it. Okay? So just as a general rule, I might try evaluating first to see if it's undefined or defined. And as we'll see later, there's also another thing that we can do to determine that as well. But let's look at the theorem that we just kind of developed here. It's not proven by any stretch, but our basic theorem is this. The first thing we have to ask ourselves is, does the limit actually exist? And this theorem tells us how. The limit exists if and only if That's what the IFF stands for, if you remember your geometry, doing that stuff in geometry. The limit exists if and only if the right and left-hand limits exist and are equal. Okay? So both of them have to exist and both of them have to be equal. Okay. So in the above example, the limits both exist, but they're not equal, so the limit does not exist. Alright, so here's another case. We're going to again look at the limit as x approaches 0, but we're going to look at our parent function for the radical functions. And the domain for this, because on our graph we can't take we can't deal with imaginary numbers, our domain is going to be x has to be greater than or equal to 0. So if I'm asked to find the limit as x approaches 0 of radical x, if I did try to evaluate here, what would I get? If I just plug in 0, what do we get? 0. Square root of 0 is 0, right? So, but that's not the limit in this case, so we'll see why in a sec. Okay? Let's kind of work our way backwards through this. If I approach from the right-hand side, what is the value of my function approach?
Good morning. Sorry about the interruption. Is David in the classroom?
Yes, he is.
Can you please have him report to the dean's office with his belongings?
Okay.
Thank you.
Alright, so as we approach from the right, the function approaches 0. Okay? So that's what we expected. You know, when we evaluated, we got 0. What do we get as we approach from the left? Yeah, it doesn't approach from the left. Okay? It doesn't approach from the left, so that does not exist. Therefore, our limit does not exist. Okay? So, that's as far as we got today. We're going to look tomorrow at how or when we can just evaluate to get a limit.